So, like we heard, this is a talk from last year's UPSLA, but since we happen to be here, it's a great opportunity to present. And it's going to be about Ethereum smart contracts. And since this is a small room, I will interact with you. I will pause and ask you questions throughout the talk. So this is not the best time to check your email necessarily. Of course, you're free to do whatever you want. And we'll see how it goes. So feel free to also stop me. And if you are going to derail me, I will let you know. So this is work that we did both from a research standpoint, but we're also applying it in the context of our company, DDOB, that Neville and I have co-founded the past couple of years. And this analysis is our main analysis. That's the main static analysis that we use at DDOB. So what is the paper about? It's about a static analysis that's kind of unconventional. It's a combination of symbolic analysis and value flow. So we have value flow, like a pointer analysis, something that works by just pushing values at as large volumes as possible, like doing it by joining tables in data log, for instance, in parallel with many threads, perhaps. Just produce volumes of values that you let them flow through the program. But those values are not actually just 0, 1, 2 or abstract object 01. They're actually entire symbolic expressions. So that's the symbolic nature. It is an analysis that's pretty precise, and the domain of smart contracts, which are small programs, let us be quite precise. And in fact, it's a path-sensitive analysis, as we're going to see. So it takes into account the logical conditions. It tries to have a symbolic reasoner, a theorem prover that will satisfy the logical conditions. It mixes values and symbolic expressions, like I said. So it is fundamentally a data log fixed point computation, but it also does symbolic reasoning. And it gets scalable precision through a mechanism that I will describe that we call dependencies. It's a generalization of context sensitivity. So that will be our main technical emphasis in this talk. There are other elements mostly in the paper, but in this talk, we'll talk quite a bit about dependencies. And obviously, it's applied to Ethereum smart contracts. Who knows what a blockchain is? Some people do not. Really? Okay. So Ethereum is the largest or second largest blockchain by value, depending on how you count. What's a blockchain? It's a decentralized ledger. Ledger means just a list of transactions. Just like the ledger that your local authorities, like your town or your state or whatever, has that says this house or this piece of property just got sold by X to Y. The discovery of blockchain, the invention of blockchain, was that we can keep such ledgers without actually having them in any centralized location. So there's no central depository. There's no central authority that keeps this ledger. How do we keep it? In a peer-to-peer network where we all grow the ledger and we all agree on the contents of the ledger. Who is all? It could be many thousand people, meaning machines, worldwide. So that's the blockchain, a long list of transactions secured by cryptography. It's not attackable, forgeable, for various reasons that we're not going to get into here. And obviously, it can list things that have financial value. That's the point of keeping a ledger, that we know transactions, we know what moved where, we know how much money or what I have in every asset, what every party has in every asset that's supported on the chain. Now, the first blockchain was Bitcoin. You may have heard of it. The second most popular one is Ethereum. And Ethereum introduced one very simple idea, which is if I have this shared memory, this long ledger of transactions, isn't this like the heap of a program? Why can't I just use this as the memory of programs? And in fact, Ethereum introduced the idea of smart contracts. They are arbitrary programs. They live on the blockchain. They are installed as part of the big ledger. Their memory lives on the blockchain. It is part of that big ledger. So smart contracts are just complete programs persistently stored on the blockchain, both their code and their state. They manage accounts, because that's why we have a blockchain. So the smart contract can be an entity and can say, this is what I have in this currency, this is what I have in this other currency, and they have logic. So they can actually perform whatever financial operations we want. In practice, smart contracts have been used to do all sorts of finance, whatever traditional exchange, bank, whatever financial organization would do has probably been done by now in smart contracts, including several pretty exotic operations. So you interact with them by calling them and starting a transaction. Now, first high-level point, and maybe half of you here are already on the same boat. If you care about program analysis or verification, you should be targeting smart contracts in your work, because these are programs for which correctness is crucial, and then you have amazing availability. The code is public. All past executions are public. You don't need anyone to give you test cases or anything. You can see every execution that everyone has performed in the past. All the current state is public. It's the running program. Everything is there. It's public. And they're programs of manageable size. So they are reduced to their essential complexity. And it is a big conceptual challenge for the research community, because we've had many, many tens of research papers, and they've had near zero impact. Obviously, there will be exceptions, and this will be one of the exceptions, what I'm presenting today. They have very little impact in terms of high-value vulnerabilities found. So what are these vulnerabilities? Anything you can imagine. Any bug in a program can be a bug in a smart contract. You could have wrong math, you could have wrong core logic, you could have some misunderstanding of language semantics or library semantics. When you interact with a service, you could be doing something wrong in the way you're calling that service. The main kind of vulnerability that our static analysis will target is the generalized form of vulnerabilities that one can call taint vulnerabilities. So every single vulnerability that we find in this, well, not every single one, but most vulnerabilities we find using this technique, they are answers to the question, can I get to this particular line in the code with this variable being controlled by an attacker? That's what I'm trying to ask every time. And of course, what is that line in the code? It can have 85 different definitions. That's about as many client analysis as we have right now in our tool suite. So it can be, can I transfer money where the recipient is something that an attacker controls? Can I do this swap in this exchange where the recipient is what an attacker controls? Can I do this other thing where the attacker controls this variable? It's all taint questions. So we don't need a specification. There's a pretty abstract specification. All I need is to identify the sensitive points in the code. So with all this introduction, getting to the point that I wanted to motivate is that there are vulnerabilities, they have high value, but research techniques have not had a very high impact yet. So this is a quote, I just picked one, there can be hundreds, but this is a quote by the top hacker in EVM networks, in Ethereum and other Ethereum VM-based networks, which are pretty much the top programmable blockchain nowadays. So this guy is the top hacker. Everyone will kind of acknowledge that. And he's saying, well, you cannot really find the bugs that matter with tooling. Tooling can give you like some shallow warnings, like don't use this, it's stupid to use block hash on the current block. Like, yeah, shallow bugs you can find, but important bugs that matter, you will never find with tooling. So what I'm going to present here is kind of an exception to that. Of course, it's still a small minority of the bugs found. So what we say in the paper from last year is that this has been used to find 6 major security vulnerabilities, gotten 350K in bounties, and there have been disclosures, there have been articles written about those, and you can certainly find them, or I can show you links, or you can get them from my presentations. So we have gotten financial bounties. We have found real vulnerabilities in financial services in the wild. And I'm not going to pretend that this is the analysis alone. The analysis is the main tool we use, but then there's security inspection by human experts. So that's also very important. But the analysis precision was key. So that was the state of the art last year, at last year's UPSLA. What do you think is the count this year? I've updated the slide. This is the slide I presented in last year's UPSLA about this. This year, instead of 6 major security vulnerabilities, 350K in bounties, it's 9 bug bounties of over 3 million total. So we found pretty significant vulnerabilities since last year's publication. And I have links to all the financial services that gave us bounties or that these have been public disclosures. It's all out there. Now, but if this works so well, why do I say nothing works? Obviously, this is still a small minority of the vulnerabilities that are being found. And it's not just smart contracts. It's pretty much everything, right? Static analysis, tooling, is not the primary way to find security vulnerabilities in any domain. From your phones to your desktops to anything, most vulnerabilities are being found by manual inspection, not by tooling. And tooling has some well-known drawbacks. So the way I would like to present this analysis is that it tries to find a sweet spot between execution-based approaches and static analysis approaches, by which I mean value flow set-based approaches. So what do I mean by that? What's an execution-based approach? Something that tries to closely simulate the control flow of the program. So this is a very blanket description. It can capture everything from symbolic execution all the way to model taking. Model taking abstracts away the state, doesn't abstract away the control flow. It still does transition by transition across all states of the state machine. So this is an execution-based approach, abstractly, intuitively. And then static analysis is, I will show it in an example, it's something that, again, doesn't capture all static analysis. Set-based static analysis are trying to be complete, but they're very imprecise. Execution-based approaches are trying to be precise, but they're incomplete. So let's try to go through an example. I have code here from an imaginary simplified contract. And here I say there is an address admin. And I have some function withdraw token. And it takes as parameters token, amount, and address to send to. And any analysis approach will try to exercise this code in all possible conditions. Everyone is trying to find all bugs, right? So an execution-based approach will do it by keeping track of the current execution. And what is the current execution? It's something that links together all the current elements of the state. So if you've written papers about that, there's a concrete or an abstract state, and it will include things like the program counter, stack, and heap. Meaning that all the variables that we've highlighted there, they are linked together. I have here things like what token I'm currently trying, what kind of money I'm currently trying, what's the amount that the external user has supplied here, what's the adjusted amount, what's the address to send to. And I'll take one value for each one of them, and the values will be linked. Are these values truly linked? Adjusted is certainly linked to amount. It gets computed directly from amount based on a mathematical formula. But token is completely orthogonal to amount and adjusted. Send to can be completely orthogonal to token. So why am I keeping these dependencies here? Why am I doing execution-based analysis, keeping a single value for token and send to an admin based and combining this with the amount for adjusted? That's what I mean by execution-based approaches are trying to be horizontal. They take these very long tuples of all the state in my current context. It's as if all of those are linked. In contrast, a set-based static analysis approach, what one might call a value flow analysis, like a pointer analysis, is something that tries to be a lot more general and scalable, but loses almost all precision. So what do I mean by that? A set-based static analysis will just say, well, amount, when I get to this point, I have determined that amount can have these three possible values, 1,500 or 30. How have I determined that? We don't care. Maybe those are just values I fuzz. Maybe these are values that I've gathered from anywhere else. You just take it from me that I'm trying in my analysis these three values for amount. Well, obviously 1000 for amount gives 1030 for adjusted amount, but the analysis doesn't know that. All that the analysis knows is that it gets from the values of amount the values of adjusted, but it doesn't match them one for one. It just says, these are the possible values for adjusted, these are the possible values for amount, these are the possible values for token. What's their combination? Cartesian product. Anything with everything. And that's quite good because you don't have state explosion. Your states are not combinatorial, but it's quite bad because you don't have any precision. So what we're trying to do here with symbolic value flow analysis is add some dependencies. We're trying to infer which of these state variables are linked to each other, that adjusted should be linked to amount. So this 1030 for adjusted should only go with 1000 for amount. This 515 should only go with 500 for amount, but not for anything else. For the most part, our analysis is a set-based analysis. But it tries to keep precision by finding the dependencies between some key parts of the state. What are these key parts of the state? That's kind of irrelevant because that's tunable. But in practice, in our case, it's the arguments of the most recent function. It's the most recent thing that you read from the blockchain, and it is who initiated the transaction. It's at the very least these 5 elements of state. Anything that depends on those, I'm keeping these dependencies. So that's kind of the main thing that gives scalable precision. But like I said earlier, the analysis is kind of different also because it's an analysis that doesn't have just values. It has complex expressions. Expressions can be things like end of some constant with a div of some variable. And this variable is any value that an owner of the contract can supply. So we have symbolic variables and we create symbolic expressions and we let them flow to program variables. So X can have all of these values. Y can have all of these values. So that's the symbolic value flow part. It's value flow, so it's kind of massive. It operates at the level of sets, but the actual values are symbolic expressions. And if you add dependencies to that, the numbers grow by a couple of orders of magnitude. So in fact, what we end up having inside the analysis is X can have the value 0 if Y has the value 0 and Z has the value 1, and the caller of the initiator of the transaction is the owner. X can have the value symbolic expression, owner value is greater than 0 or greater or equal, or 0 is less than the owner value if Y has the value owner value and caller is owner, for instance. So we have such values throughout the analysis, and the values are kept under these dependencies, and we end up with millions and millions of inferences that simulate, that model what the program can possibly do, but not line by line, in a massively parallel set-based way. And in fact, in the paper, you will see a little more detail because there are a couple of kinds of dependencies, like global dependencies for local variables and global dependencies for things that you can think of as global variables, including the initiator of the transaction. So implementation-wise, this analysis is implemented using data log-based analysis rules. So it does try to join tables as efficiently as possible. It appeals to a symbolic solver, a theorem prover, that's also expressed as data log rules. That's not necessarily the best choice. It might be great, other than engineering, it might be great to have a different symbolic solver for logical conditions to tell me when something is satisfiable. But for now, it's fine. The theorem prover does some limited top-down reasoning. So it does some search to try to satisfy some equations or inequalities very simply. But most of its work is bottom-up reasoning up to a bounded expression size. What does bottom-up reasoning mean? All the true theorems. You can imagine if you're trying to prove all the true theorems, you cannot go very deep. I mean, we have basically something like 4 rounds of expressions of up to depth 5 or something, and then they get simplified and we have another round. But you cannot prove too many things if you're trying to prove all valid propositions. So schematically, this means that there's a big fixed point logic that primarily gets all the true statements through an implies or equals from the symbolic reasoner. But every now and then, when it finds something that it really needs to cover and it cannot cover it with simple means, it makes an equality request or inequality request and expects a response. And that's the top-down reasoning part. But that's much more limited, much less expressive in what theorems it can prove compared to bottom-up reasoning. That truly has pretty good theory for the arithmetic operations of Ethereum. Okay, so don't know what happened here. Could it be that my stick out of memory? Okay.
Close the other tab.
But we certainly should not close the remote water. So yeah, we can close the previous PDF tab. That would be good. Yeah, that should give us some memory. Excellent. Thank you. Okay, so yeah. Sorry about that. Okay, so an interesting part of this paper is that we have developed what we think, obviously it needs updating, but what we think is a pretty good benchmark suite for evaluating contract analysis. So this is freely available. I encourage you to experiment with that. It's some normalized benchmarks, but also they include not just seeded vulnerabilities, but also arbitrary contracts from the real world that do not have vulnerabilities. They are actual deployed contracts with high value, where you can control your analysis against those and see whether you're truly not reporting vulnerabilities on those. So we encourage use of this benchmark suite. We compare to kind of the best known tools out there. Obviously, that's a moving target. I cannot claim that the comparison will always be the same, but the main idea is that what we get is, compared to a symbolic execution tool versus a hybrid symbolic static analysis tool, we get much higher completeness. We get pretty good precision. So 82% of our warnings are actual warnings. Of course, symbolic execution will get 100%, but we're not that far behind. We are much better than traditional static analysis or hybrid in terms of precision. We get very good scalability. We get a very scalable analysis, and average runtime that's pretty good. Every static analysis is evaluated in the 3 dimensions of completeness, precision, scalability. And in all 3, we're doing very, very well with this, which is exactly the design goal of that. So to conclude, this is an analysis that shows how combining symbolic reasoning and value flow reasoning is extremely promising. We try to keep the precision by employing dependencies. They are a generalization of what is in static analysis called context sensitivity. But instead of context sensitivity in the sense of keeping who called me or whatever, we keep dependencies on specific values and what inferences depend on other variables having these specific values. That's the dependency part. And the higher level picture that I want to transmit to you is that the domain of smart contracts is a challenge, but analysis innovation can meet this challenge unexpectedly. The experts didn't think that we can kind of do that. And I'm running out of time, of course, and I had overflow slides, but I absolutely want to say one thing and then I'll take questions. So I'm not going to go through all of this, but there are many lessons for static analysis in industry versus academia. And I want to propose 2 things that are surprising, especially since this is kind of an older talk from last year, and one has the ability to look back a little. First of all, in research papers, we may have some wrong metrics for the things that count. And I want to ask you, in terms of false positives, the standard metric for precision, what's the difference between an analysis that has 99% false positives and an analysis that has 99.9% false positives? Is the small difference, a big difference?
Depends on scale. If you're at very low
For
scale,
smart contracts.
well, smart contract.
Yes, for actual security vulnerabilities, not just unused return value, like something that could actually have monetary impact. This looks very close, right? This is 10 times worse. To find a true vulnerability, you need to inspect 1,000. To find a true vulnerability, you need to inspect 100. And obviously, we don't want to inspect even 100 to find a true vulnerability. Like, people get tired. But in academic papers, we say, oh, 60% false positive. Why don't you make it 10%? Why can't you make it even better? And that's entirely meaningless, because 95% false positive is an amazing practical result. If I can get something that will give me money by inspecting just 20 warnings, I can do that in 2 days. 95% false positive doesn't get you a paper, but it gets you really high value vulnerabilities. And I'll stop with this and take questions. And clearly, to supplement that, when you look at planted vulnerabilities, when you look at things that are likely to have vulnerabilities, you do want much lower false positives, like in this case, 18%, not 95%. But when you're looking at contracts in the wild, 95% false positive, 5% true positive, it's perfectly acceptable. Okay.
Thanks for the talk. We would like to circulate the mic, so for questions. We don't have another mic.
Oh, okay.
Yeah, you can speak.
You can speak in
Yeah,
this.
no problem.
Great talk, Alice. I mean, a late lunch was worth it. So, so the things you mentioned are pretty relevant for program analysis in general, like for regular programs, not just for smart contracts. I mean, you are doing execution list analysis, or you're doing set-based static analysis, and this is the problem you face even in regular programs. My question is that how do you do this partitioning, right? Is there something smart contract specific where you figure out what should be tracked together and what should be a set-based thing?
I think that the big difference between smart contracts and, like, say, if we were to analyze Java programs, Android, iPhone, whatever, is the size. They're already modularized. They're 24 kilobyte binaries, every smart contract. So this is a path-sensitive analysis. It tries to prove all the logical conditions and all the ifs, all the whiles. I cannot do this for Java. I cannot do this for large programs. So that's not exactly your question, but that's why I would not try to do path-sensitive analysis on enterprise or mobile software. But for smart contracts, I would. How would I use these exact techniques in enterprise or mobile software? I would use them by first trying to find an appropriate modularization of the code. To say, here's how I split it. Here's how I split it in small parts. And I will lose precision in the interactions between the small parts. But for some reason, I've done a good definition, so I don't care about the precision I'm losing there. If you can give me that modularization, yes, you can apply this to anything. So it's not really that the dependencies idea does not work. It's that one would need to think much harder to get this to scale.
So my question is that I think I missed that part about dependencies. So how do you figure out the dependencies? Which variables are dependent, which are not?
It's pretty arbitrary. It's a pretty arbitrary heuristic right now. So what I said is that right now our heuristic is that we keep dependencies on the variables of the last function call, the transaction initiator, whether I was called by the owner or an untrusted user, and the very last thing that I read from the blockchain, the very last S load, the very last load I did from storage.
So that is something very specific to smart contracts.
One can think of the blockchain as the heap. So I could do the same thing. I could do all the local variables. The last thing that I read from the heap, anything that depends on it, I remember what value it depended on. and then trusted or untrusted external caller. I could do the same thing for, say, Java.
Sure, makes sense. Thank you.
We'll take one more question.
Thank you. It is a very interesting talk, and specifically, we have the dependency, you reduce the state space very significantly. And then I have comments regarding the dependency. So I don't know if you have your future work that you wanted to like explore this dependency. So I have two observations while we read the contract. The first one is actually we specifically focused on the storage variables. Storage variables is actually the part that is in the global blockchain state machine. So they actually affecting the whole state machine in the global in the blockchain state. So that's the first thing that we might be able to narrow down the scope of what the variable we actually care. So the second thing is that it's actually that these variable I mean, these variable dependencies, they might be sometimes be very specific or decipher that is actually a arithmetic expression, or sometimes it's like a equation relation between these variables. So maybe if you have the plan that in future that you're going to like explore a little bit more about this dependency, that maybe more specific. And,
I think there's definitely a lot of space to improve what one is keeping for dependencies. I mean, right now it's a local fixed point. What we have. Certainly, if I keep, for instance, with the current setup, if I just go blindly and say, I want to keep the last two storage variables, storage values that I read, it's not, scalability will suffer tremendously. So, I mean, we have experimented with shallow things, but if one can be a little more clever about what values are worth tracking all the dependencies of, yes, sure, I can see it being having like much better policies than our current standard policy.
just one more. So actually, sometimes if we track this dependency relation in terms of their values, sometimes we might be able to infer the actual algebraic relationship between the variables. That's something might be very valuable to us.
Yes, that might be the case. In fact, for simple expressions, this will just happen naturally anyway. Just because all our values are symbolic expressions. And if something, it's not that we keep, the symbolic expressions are not over-programmed variables, but some of them, like this owner value, it probably came from a public argument of a function. So it is like a synonym for that public argument. Not exactly, it's a value, not a program variable. So one could probably get some benefit in the future if they tune the whole analysis to actually keep track of program expressions over some very specific variables, though, not local variables, just some key variables on the boundary of what an external caller can access.